Hello, we are the large-scale lunar prospecting rover Team 2, and this is our design day presentation. I am Eric Hall, I'm the team lead. Our team members consist of Jacob LaRue, Parrish Ballinger, Brady Tober, Oliver Smith, and Tala Al-Saidi. This is our design day poster. In this presentation we're going to be going over the results of testing, our prototype construction, and the materials we used. The idea behind our project is to develop a concept for a semi-autonomous rover capable of prospecting over large areas and developing a resource map. This rover is designed to operate on permanently shadowed craters in the southern lunar surface, which means low light, very low temperature, high radiation environments. And it has to be able to detect subsurface and surface resources, including oxygen, water, aluminum, iron, silica, and platinum.
Project goals are to design a semi-autonomous rover that will prospect the lunar South Pole. This means that it must operate in craters that are permanently shadowed, where the sunlight does not reach. This makes the rover mission immensely more complicated because there are extremely low temperatures and we cannot rely such as things as solar panels or recharging batteries via solar panels because the rover would not have access to those resources. This is again made more complicated by the fact that the rover would be looking for subsurface and surface resources, which means that it could also be searching for things that are not visible on the surface of the moon. Per the RASCAL competition guidelines, which is hosted by NASA, our sponsor, and which we are competing in, the rover is intended to operate from anywhere from 1 to 9 months. Last semester, we worked on the conceptual design for our rover. This means that we created a full design for an actual idea that could be created if it won the competition. In our design, the whole rover is powered by an RTG, or radioisotope thermoelectric generator. This provides both heat and power to the vehicle. We also have numerous instruments for both prospecting and navigating the rover, such as the Sherlock, RIMFAX, Mastcam-Z, and other instruments. In terms of mobility, the rover will have 6 non-pneumatic tires that we also designed, which will be held together by a damped suspension system. The body of the rover will be rectangular and made of a titanium alloy that we chose. This provides both stability and insurance against tipping, as well as helps to navigate heat to the places where it needs to be the most. Shown here are some images from last semester. The top left shows a conceptual design of our entire rover with all systems attached to it. Below that is an analysis of our rover under certain loads. The red areas indicate the area of most deformation, which only turned out to be a few millimeters. This is mostly due to the fact that our titanium alloy is relatively thick in some places. The right side shows another portion of the work that went into designing the rover by showing all the power, voltage, and current that needed to be supplied to different components. This took a lot of work to balance and make sure that everything was in accordance as it should be.
This semester we focused on building a prototype that's quarter scale, that showcases navigational capabilities, that uses map terrain using NVIDIA Jetson Nano as the brains, LiDARs, and depth sensing A cameras. This prototype is currently remote controlled, but we are currently working to get the rover to be autonomous by design day. The frame is made of T-slotted aluminum extrusion. The side panels are also aluminum composed of 1/8 inch. The frame is connected via brackets, sliding knots, and screws for mounting. The LiDAR and depth cameras mounted directly to the side panels. The drivetrain is composed of 6 brush motors, 2 electronic speed controllers, and an RC receiver powered by 2 batteries. Our prototype has 6 wheels to emulate our conceptual design, and the tires are 8 inches pneumatic tires.
Before we move on to the software portion of this video, it is important to discuss some of the other things that have to do with the hardware and body of the rover. Firstly, you can see above that there is a budget showing the total expenses and the remaining budget that we had. As is mentioned on our poster, we were well under the budget of $3,000, almost by nearly $1,000, and we did have time to order extra parts besides. The bottom pictures show the frame of the rover during construction and after construction. The left one shows the completed frame bracketed and bolted together as mentioned, while the right side shows Eric, Tala, and Oliver constructing the frame at Eric's house. The video shown also demonstrates that the rover was able to move under its own power in the early stages of testing, something that was a goal for us to achieve.
So this is the software implementation for the Lunar Rover. And for software, we have two main devices. That's the depth sensing camera, the Intel D435, and a LiDAR sensor from SlamTech. That's the A1R8. And these are both sourced to ensure that they're compatible with the Jetson Nano. And to run these devices, we have to use ROS, the Robot Operating System software library, and specifically the ROS melodic distribution because it's compatible with Ubuntu 18.04, and that's the operating system that's ran on the Jetson Nano. To map what the LiDAR sees, we also have to run Hector SLAM, simultaneous localization and mapping. And what this does is it extracts the RP LiDAR data into a mapping format with pathing capabilities. So these are the displays for both the devices we're using. In the bottom right, we have the Intel D435 RealSense depth camera. It's got a 4-meter range, and it has both a depth and RGB streaming capability. And to run the device, we have to use the Intel RealSense SDK, which is provided by the manufacturer. And the top right is the Hector SLAM LiDAR mapping as well. And in regards to the controlling of the motors, we have one electronic speed controller on each side of the Rover, covering 3 motors. And there's individual batteries for the Jetson Nano, as well as each side of the motor system. So there's 3 onboard batteries. And our testing plans. So the first test experiment we've already done, and it's placing the rover in a desert landscape and showing successful implementation of LiDAR and cameras for obstacle avoidance and mapping. And it's able to display a map of terrain traversed by the rover, shown by this image at the bottom. And then the second test or experiment is dependent on our capability to get autonomous control. What it will do is place a spread of target objects in front of the rover and detect the most concentrated presence of target objects, and displaying a map of the resource density of the terrain traversed by the rover.
Here are some further pictures to demonstrate the software section of our rover. The left picture shows the setup that we were using to receive the data from the LiDAR and camera. The monitor is connected wirelessly to the Jetson Nano, which is sending the LiDAR mapping and camera vision to the monitor, which we can then see. The right picture shows the wiring that is making this happen. The wheels and motor are wired into a hole that goes up into the body of the rover, which is then connected to the Jetson Nano, speed controllers, and other instruments. The video playing is showing the live mapping of the LiDAR as well as what the camera is seeing. As Eric pulls the rover towards him, we can see that the mapping of the backyard is happening in real time. We can see that it is extremely accurate. It's measuring all the pillars, chairs, and even the shape of the fence around it. And so we can see that our technology does what we intended it to do. This concludes the large-scale Lunar Prospecting Rover Team 2's video for Design Day. We thank you for listening, and we look forward to seeing the judges and all members of the public on April 29th.